Well, students, we have finished our discussion on polynomial interpolation. In this lecture, we will study another interpolation technique, which is not polynomial, but piecewise polynomial. From our previous lectures, we have seen that quite often the polynomial interpolations will be unsatisfactory as the approximation tool. This is particularly true if we insist on letting the order of the polynomial to get larger and larger, right? However, if we keep the order of the polynomial fixed and use different polynomials over different intervals, with the length of the interval getting smaller and smaller, then the interpolation can be very accurate, and hence this can be a powerful approximation tool. So such approximations are called piecewise polynomial approximations. Let me explain this idea a little more clearly. Assume that you are given the nodes x0, x1, and x2, and you have some function f whose values at these nodes are also given to us. In other words, assume that we are given this data set. With this, you can construct a quadratic polynomial P2 of x that interpolates the function f at these points, right? Instead of that, what you do is you take these 2 points and generate the polynomial P1 of x in this interval. And similarly, you take these 2 points and generate another polynomial P1 of x, okay? To distinguish between these 2 polynomials, let us denote this by P11 of x and denote this polynomial by P12 of x. Now you define a function P of x is equal to P11 of x in the interval x0 to x1 and P12 of x in the interval x1 to x2. Assume that the graph of the function is something like this, where this is the point x0, f of x0, and this is the point x1, f of x1. Now P11 of x is just this linear polynomial, that is the straight line joining these 2 points, right? And P12 is the straight line joining these 2 points. Now you can see that the interpolation conditions are satisfied. That is, P of x0 is precisely f of x0 and so on, right? P of x1 is equal to f of x1. P of x2 is equal to f of x2. So interpolation conditions are satisfied, but it is not a polynomial. It's only a piecewise polynomial. Therefore, this is a piecewise polynomial interpolation for the function f of x. Similarly, if you introduce another point, say here and here, and provide the information about the function value at these points, what you can do, you can find similarly piecewise polynomial in each subinterval, and thereby you will have the piecewise polynomial like this and like this, right? And then one polynomial is like this, and then you have like this. And you can see that this is a piecewise polynomial again, and this is little more accurate than the piecewise polynomial that we constructed with x0, x1, and x2, right? So like that, if you go on increasing the number of partition points in the interval, you tend to get more and more accurate interpolating function, which is a piecewise linear polynomial function. In fact, you can think of constructing piecewise quadratic polynomial function, piecewise cubic polynomial functions, and so on. You need to have adequate nodes in every subinterval to generate these kind of polynomials. Let us construct piecewise linear polynomial explicitly and see how it comes out. For that, let us consider the nodes x0, which we will take as A, and some point x1, which is between the points A and B, and x2 is taken to be B. Of course, with these node points, we can obtain a quadratic interpolation, but instead we will go for a piecewise linear polynomial interpolation. So you have x0 to x1 as one interval, and in this interval you will construct p1 1 of x, and you have another piece of interval x1 to x2 in which you want to find p1 2 of x, right? Let the function values be like this: f of x0, f of x1, and f of x2. Now you just need to write the first order interpolating polynomial in the interval x0 to x1, which is nothing but the line joining these 2 points, right? So you can also write it in the Newton's form or Lagrange form. Here I am writing it in the Lagrange form. Similarly, you can take the second part of this interval, that is x1 to x2, and write the Lagrange form of interpolating polynomial or Newton's form and get p1 2 of x, and that is given by this expression. Well, I chose to write in the Lagrange form again. Now define the piecewise interpolating polynomial, which we denote by s of x or p of x, which is nothing but you just patch these two polynomials together in such a way that in each interval you have the corresponding linear polynomial. So that's the idea. So this is the graph of the function s of x. Similarly, suppose we give point x0, x1, then this is x2, this is x3 and x4. What you can do is either you can form a 4th degree polynomial interpolating the function f of x, or you can stick with each subinterval and get p1 1 of x. Here you can get p1 2 of x. Similarly, here you can get p1 3 of x, and finally here you can get p1 4 of x, right? Or even what you can do is you can take these 3 points and make a p2 1 of x, that is the quadratic polynomial in this interval, because now you have 3 points in this interval x0 to x2, therefore you can make a quadratic polynomial here. And similarly, in this interval, that is from x2 to x4, you again have 3 node points. Therefore, you can make another quadratic polynomial in this. And you can therefore define a piecewise quadratic polynomial also. Similarly, if you have more points, you can go for higher degree polynomial in the respective subintervals. Like that, you can get the approximation more and more better by fixing the degree of the polynomial but decreasing the length of the subintervals. The main advantage of this is that your degree of the polynomial is fixed, therefore your arithmetic error will be greatly controlled. At the same time, you get more and more better approximation because you are putting this approximation in a smaller and smaller interval, and thereby you have a better approximation to your original function. That is the main idea of piecewise polynomial interpolation. Let us have an example. Recall that we have obtained a quadratic polynomial p2 of x for this data set at the beginning of this chapter, and the quadratic polynomial is given by this expression. Now you can also find a piecewise linear polynomial interpolation for this data set, where in this interval you get this expression, and in this interval you get this expression. You can just put these values in our previous formula and immediately derive these expressions. And if you recall, these data are generated from the function f of x equal to sine pi by 2 into e power x. Now, my interest is to find the value of this function at x is equal to 0.25 and also at x is equal to 0.75. That is a point in between this 0.25 and another point somewhere in between this interval 0.75. You can see that the exact value of the function f at x equal to 0.25 is given by 0.902117, and the value generated by the quadratic polynomial, that is this polynomial, is given by 0.881117. And the value generated by the piecewise linear polynomial, where we have to put x equal to 0.25 in this expression, and that gives us 0.762105. You can see the relative error in these two numbers when compared to the exact number. So you can see that the quadratic polynomial had around 2.3% error, whereas the piecewise polynomial had 15% error. So in this interval, P2 was doing well. And let us go to the other part, x equal to 0.75. In this interval, at this point, again, you can find the exact value, the value generated by the quadratic polynomial and the value generated by the piecewise linear polynomial, in which case you have to put x equal to 0.75 in this expression. You can see that the relative error in P2 of x when compared to the exact value is around 61%, whereas the relative error in the value generated by the piecewise linear polynomial is 3.8% when compared to the exact value. Let us see this graphically. In this graph, we are showing the graph of the function f of x by blue solid line. The magenta solid line is the quadratic polynomial interpolation, and the red solid line is the piecewise polynomial interpolation. You can see that at the point 0.25, the piecewise polynomial interpolation is giving a poor approximation, whereas the quadratic polynomial is giving a good approximation. Whereas at the point x equal to 0.75, the situation is just opposite. The linear polynomial is giving a good approximation, whereas the quadratic polynomial gives a poor approximation. This shows that in general, you cannot say that one performs better than the other, and any graphical observations are not going to give us guarantee about how good the interpolant approximates the given function at all the points in the interval in which we approximate. Here, the piecewise polynomial interpolation giving a better answer is merely a coincidence. And similarly here, the quadratic polynomial interpolation giving a better answer is also merely a coincidence. Therefore, we cannot make any conclusion that piecewise polynomial is always better or some global polynomial approximation is always bad or vice versa. You cannot make any conclusion. One needs to properly do analysis in the respective problems and try to understand what is going on as per their situations. But what we can say is, as you go on decreasing the length of the interval, that is xi plus 1, this length, if you go on decreasing, let us denote this size by h, and the corresponding piecewise polynomial, let us denote by s of x, then what you can show is as h tends to 0, sh of x tends to f of x in some sense. So in that sense, fixing the degree of the polynomial and increasing the number of points in the partition gives better results in the approximation. Let us do this convergence analysis in a little bit more rigorous way. Let us form a sequence of piecewise linear polynomial approximation to a function f in an interval ab. Let me explain to you how to form this sequence in a graphical illustration. Let us consider a function f of x whose graph looks like this. And let us take this function in the interval a to b, which we will take always as x0 and xn respectively. Let us first take n is equal to 1 and consider the polynomial interpolation for the function f of x. In this case, it will be a polynomial of degree 1, and generally we represent it by p1 of x, right? And its graph is given by this straight line. It is p1 of x. Well, since your given nodes are just x1 and x2, you can also interpret it as piecewise linear polynomial interpolation, where you have only one piece of interval, therefore you have only one linear polynomial, right? Now let us introduce one more point in our set of nodes and call that as, say, x1. Therefore you have x0, x1 and x2, which is b. With this we can obtain two linear polynomials, one in the interval x0 to x1 and another in x1 to x2. Patching them together, we get a piecewise linear polynomial. Let us denote it by s2. Let us draw the graph of this piecewise linear polynomial s2, whose graph is given like this, which is obtained by patching p1 1 of x, which is a linear polynomial interpolation in the interval x0 to x1, and p1 2 of x, which is the linear polynomial interpolation for f of x in the interval x1 to x2. Similarly, you can construct the piecewise linear polynomial s3 of x by introducing one more point anywhere in this interval. But for the sake of simplicity, we will assume that the length of the subintervals are equal. In other words, we will consider equally spaced nodes in our discussion. This is just for the sake of simplicity. Let me now draw the graph of the piecewise polynomial interpolation with 4 subintervals, which is denoted by S4. So if you take 4 nodes, that is one introduced here, which is x1, then this becomes x2, and here x3, and now the last one will become x4. Thereby we get the piecewise linear polynomial interpolation S4. Let us draw the graph of S4. The graph of this S4 is given like this, and it consists of 4 pieces. One is P1 1 of x, which is in the interval x0 to x1. The next one is P1 2 of x, which is in the interval x1 to x2. And then this is the linear polynomial interpolation P1 3 of x in the interval x2 to x3. And finally, this is P1 4 of x in the interval x3 to x4. All these 4 patched together gives us S4 of x, right? Similarly, we can introduce x0, x1 up to xn and get the piecewise linear polynomial interpolation Sn of x, which is given by P11 of x for x in x0 to x1, P12 of x in the interval x1 to x2 and so on, P1n of x in the interval xn minus 1 to xn. So that's the way we construct the piecewise polynomial interpolation Sn of x, where we will take xk to be a plus kh, where k is equal to 0, 1, 2 up to n, and h is defined as b minus a by n. So for every fixed n, we have the function Sn of x. Thereby, we have a sequence of function Sn defined in the interval ab. Now the question is whether this sequence of functions converges to f pointwise. Remember, in the interval xk minus 1 to xk, f is approximated by the linear polynomial interpolation P1k of x, right? The mathematical error for this P1k of x when compared to f of x is given by ME1 of x, right? And that is nothing but f of x minus P1k of x. And we know the expression for this mathematical error from our theorem on mathematical error for polynomial interpolation, and that is given by f double dash of some xi k divided by 2 factorial into x minus xk minus 1 into x minus xk, right? And this holds for all x in the interval xk minus 1 to xk. This is the error involved in the linear polynomial interpolation in one subinterval. Don't forget to mention where this xi k belongs to. Well, xi k is an unknown point between xk minus 1 to xk. Now let us assume that f is a C2 function defined on the interval AB. Then we can write, then f double dash is a continuous function. And since it is defined on the closed and bounded interval, we can always find a m such that modulus of f double dash of t is less than or equal to m for all t in the interval AB. Right? So let us use this fact in the expression for the mathematical error to get mod ME1 of x is less than or equal to m by 2 into mod x minus xk minus 1 into mod x minus xk, right? Again, if you recall, we can dominate this term by finding the maximum of this function. By fixing this function at the maximum point, we can see that x minus xk minus 1 times x minus xk can be less than or equal to xk minus xk minus 1 the whole square by 4, right? This idea is already discussed in one of the examples in the previous class, therefore I will not repeat it. We will put this upper bound here, and thereby we will be freezing the variable x in this term, and that gives us precisely the estimate for our mathematical error for any x that we plug in into the mathematical error, right? So that gives us that mod ME1 of x is less than or equal to m by 8 into mod xk minus xk minus 1 the whole square, right? We have taken xk as xk minus 1 plus h, right? Well, we have written xk is equal to a plus kh, but that precisely comes from this expression, right? Therefore, this is equal to h, and that I will put in this to get m by 8 into h square. So recall that we have proved mod f of x minus p1k of x is less than or equal to m by 8 into h square for all x in the interval xk minus 1 to xk. Now, we can use this to see that mod f of x minus Sn of x, that will be equal to mod f of x minus p1k of x, x belongs to xk minus 1 to xk for some k, right? You give me any x in the interval ab, I can always find a k such that x belongs to xk minus 1 to xk. Once you find such a k, you can write f of x minus Sn of x as f of x minus p1k of x, right? And that will be less than or equal to m by 8 times h square. Since this holds for all x in the interval ab, we can write it as the infinite norm of f minus Sn is less than or equal to m by 8 into h square. Now this implies that as h tends to 0, right, which is equivalent to taking n tending to infinity, right? Because if you recall, we have taken h is equal to b minus a by n. So you take n tending to infinity, it means you keep on increasing the number of nodes in the interval AB, thereby you are shrinking the length of each subinterval. And in the limiting case of n tending to infinity, you have h tends to 0. And in this case, you have Sn tending to f uniformly, right? So this proves the convergence of the sequence of piecewise linear polynomial interpolation to the function f. You can in fact prove in a similar way the convergence of the sequence of piecewise quadratic polynomial interpolation, piecewise cubic polynomial interpolation, and so on.